Hello. This video is about prime fields and the concept of characteristic. And prime fields are smallest possible fields. So the story is the story of just something which is inevitable in a field. The element 1, the identity under the multiplication. Any field should have such an element. And if we have an element in a field, or even more generally in the ring, we can perform addition operation with it. And if we just take this element some number of times, well, let's call it n, this number of times, and add it with itself, we will end up with something which we might consider as the natural number n, and now it sits inside our field. Similarly, for negative 1, if we have 1, we should have negative 1 in our field, because our field is supposed to be first an abelian additive group. And we can take the sum of this negative 1 some number of times, call it n, then we will end up with something which we might consider as negative n, and it will be an element of our field. So all in all, we have a way of assigning elements of our field to any integer. And this assignment is very easy to check that this assignment defined this way is a homomorphism. So this is a ring homomorphism. What I just said applies to all rings, not even commutative, but just all rings. And this ring homomorphism will be possible if we start with a ring which is containing unit, which is a unital ring. So any unital ring comes equipped with a natural because it is defined in such a natural way, natural homomorphism from the ring of integers. So the ring of integers is called initial object among all unital rings. But we are looking at fields, and we will explore this field condition really soon. So right now we have a ring homomorphism according to the general principle. The homomorphism might not be a priori an embedding an injective homomorphism, and the measure of it from being injective is the kernel, and the kernel of this homomorphism will be an ideal in the ring of integers, and we know these ideas pretty well. They are principal, but I want to distinguish between the two drastically different situations. So the kernel is 0 and the kernel is non-zero. If it is non-zero, it's a principal ideal generated by single element. I will call it P. I will justify my choice for this name in a second. But if it is 0, then we have no kernel, we have an embedding of this ring of integers into our field. And since it is a field, we should have inverses to all integers. And allowing for inverses, we will have a field of rational numbers sitting inside F. So the field of rational numbers is the smallest field containing Z, absolutely smallest field containing that. And that is a situation if we don't have any kernel. So that is called the characteristic F being 0 case. The other possibility, or the other possibilities is that we do have a kernel and it must be generated by a single element. So let's look at this natural number P. What can it be? I argue that it cannot be a composite number. It cannot be a product of two numbers bigger than 1. Then, if it is, then we would be saying that this product is equal to 0 in our field. So we'll have two zero divisors. That is impossible in a field, so P has to be prime. And then we have a situation that our integers, quotient by this ideal, sit inside the field F. So that quotient is a field. It is a field of P elements, and it should be a subfield of our field F. That is the case of finite characteristic of characteristic P. So let's look at it again. In the first case, the subfield in our field F generated by 1 additively and multiplicatively is the field of rational numbers. That is the case of characteristic 0. In the second case, the subfield in our field generated by element 1 is this field, is the field of P elements, and that is the case of finite characteristic. So independently or not so independently, the characteristic is just the smallest number of ones which is equal to 0, and that is this inevitably prime P. And if it is not possible to find a sum of ones which is equal to 0, then the characteristic is declared to be 0. As an immediate application, let's look at the following problem. So one instance of this problem is the following question. Can there be a field of 6 elements? In general, this application will address the question of what are possible cardinalities of a finite field, finite fields. Let's assume that our field is finite, and then inevitably we should be in the second case. We cannot be in the first case, because if we only have finite number of elements, there must be a sum of ones which is equal to 0. So then inevitably the characteristic of our field, the smallest number of ones which is equal to 0, is also finite. So it must be in one of those cases. We must be in the case of a prime characteristic. So then, let's make it more specific, then there should be some prime such that the field of P elements is its subfield. Now let's turn the beautiful linear algebra on. This is a subfield in the bigger field. The bigger field can be seen as a module over this, and modules over fields are vector spaces. So F, our input field, is a vector space over the field of P elements. And the measure of size of vector spaces, dimension, has to be finite. The dimension of this field has to be finite, because if it is not, then we'll have infinite number of linearly independent vectors, and that will contradict the condition that there is only finite number of elements at all, dependent or independent. So if it is finite, we know that the field, or this vector space now, has to have a basis, has to be coordinatizable, has to be isomorphic to some coordinate vector space for some dimension d. So d is this dimension. And the rest is just the counting. So to count the number of elements is to count the number of elements in here. And we do know how to count the number of vectors. Vectors of length d with p components, p choices for each component. So that is the multiplication principle, and that is the answer. Here's a conclusion. Cardinality of a finite field can be only a power of a prime. There is no field of 6 elements in particular. All right, goodbye.